Dear students, I'm Dr. Nusrat Gul and I'm going to discuss with you today the dual nature of matter and de Broglie's relationship. In our previous lecture, we understood clearly that some properties of radiations and matter may be explained on the basis of wave nature and some properties on the basis of particle nature. ये जो यहाँ पे लिंक दिया गया है, इस लेक्चर में मैंने आपको समझाया कि जब आप वेव नेचर की बात करते हैं या जब आप इंटरफेरेंस एंड डिफ्रैक्शन की बात करते हैं तो ये प्रॉपर्टीज आपकी समझ में तभी आ सकती हैं या ये प्रॉपर्टीज तभी एक्सप्लेन हो सकती है व्हेन यू इन्वोक वेव नेचर ऑफ मैटर एंड रेडिएशंस। इसी तरह से देयर आर फ्यू प्रॉपर्टीज लाइक फोटोइलेक्ट्रिक इफेक्ट एंड सेंटिलेशन। तो ये प्रॉपर्टीज हम तभी समझ सकते हैं व्हेन वी कंसिडर light or radiations and matter to have a particle nature. In the early 20th century, the investigations and experimentations were more focused on light, and scientists bothered little about the material particles. ये जो दौर था, ये जो वक्त था, the scientists were baffled by the characteristics of light because एक single nature लाइट की कैरेक्टरिस्टिक्स को एक्सप्लेन नहीं कर पा रहा था। कुछ एक्सपेरिमेंट्स एडवोकेट कर रहे थे वेव नेचर को और कुछ एक्सपेरिमेंट्स एडवोकेट कर रहे थे पार्टिकल नेचर को। सो फाइनली व्हाट डिड द साइंटिस्ट्स प्रपोज? दे proposed the dual nature of radiations and nobody was bothered about the material particles. Material particles के बारे में कोई सोच ही नहीं रहा था। ऐसे में a French physicist came up with a bold assumption regarding the material particles. एक फ्रेंच फिजिसिस्ट था, उन्होंने कहा कि जो लाइट है जिसको कि हम वेव कंसिडर करते हैं, जिसको वेव प्रॉपर्टीज देते हैं, इट समटाइम्स बिहेव्स एज अ पार्टिकल। और क्या वजह है कि एक पार्टिकल जो है इट शुड नॉट बिहेव एज अ वेव। एंड हु वाज दिस साइंटिस्ट? He was Louis de Broglie. De Broglie hypothesized in 1924 that light that was considered as a wave can behave as a particle. Similarly, a material particle may also behave as a wave. That is, material particles may have a wave associated with them. जैसे एक फोटोन के साथ एक वेव होती है with a particular wavelength, इसी तरह से एक मटेरियल पार्टिकल के साथ भी वेवलेंथ एक वेव एसोसिएट हो सकती है जिसकी अपनी वेवलेंथ और बाकी वेव कैरेक्टर्स हो सकते हैं। He named this wave as the matter wave. So what was his suggestion? His suggestion was that everything in the universe has a dual nature. That is, it may behave as a wave as well as a particle depending upon the experiment we are conducting or the property we are studying. जैसे हमने देखा, when we talk about interference and diffraction, we consider particles as well as radiations to have wave nature. When we talk about photoelectric effect or scintillation, we consider particles as well as radiations to have a particle nature. Now, how to derive this relationship? ये रिलेशनशिप जिसमें कि डी ब्रॉय ने मैटर की वेवलेंथ को उसके मास और वेलोसिटी के साथ रिलेट किया, he derived it by an analogy with the photons. So, what he did? According to the Planck's quantum theory, the energy of the photon is given by h nu, where h is Planck's constant and nu is the frequency of the radiation. h की वैल्यू जो है 6.6 in 10 raised to the power minus 34 joule second. Or as per Einstein, rather Einstein's mass energy equivalence is equal to pc. ये जो p हमारा है ये मोमेंटम है, यहाँ पे आप उसको mc भी लिख सकते हैं, then it will be equal to E is equal to mc into c, that will come out to be mc square. So from these two equations from equation first and equation second. Left hand side में E यहाँ पर भी है, यहाँ पर भी है. So जब left hand side बराबर है तो right hand sides must be equal. That is H nu must be equal to PC. Right? Now this H nu is equal to PC. हम बचपन से पढ़ते आ रहे हैं rather from our 9th 10th classes that the velocity of the light, yeah, radiation is equal to the product of its frequency and wavelength. From this equation, we will try to find out the value of this frequency nu. This nu will simply be equal to C divided by lambda. Now, हम इस nu को substitute करेंगे equation number 3 में. H nu की जगह C by lambda is equal to PC. This C and C goes. What we are left with H divided by lambda is equal to P, or lambda is equal to H by P. De Broglie suggested that the wavelength of the matter wave associated with the particles of mass m can be obtained from the above relationship. Now, if the particle has a mass m, it is moving with the velocity v. How to get that? हम simply इस p की जगह momentum की जगह लिखेंगे mv, because we know momentum is the product of mass and velocity. So this lambda becomes equal to h by mv, where p is equal to mv, where momentum is equal to the product of mass and velocity. ये जो इसका experiment था, rather ये इसकी hypothesis जो थी de Broglie की, it was confirmed in 1927 by Davison and Germer. When an electron beam was diffracted by a nickel crystal, यानी कि जब एक electron beam obscure हुआ एक nickel crystal से, we got diffraction patterns that made it very clear कि electron के पास जो है एक wave character है. Similarly, G.P. Thomson ने भी experiment किया. उन्होंने electrons pass किए through a thin metal sheet. He also observed that those bright and dark fringes that advocate the this wave nature of the electrons or material particles. It is not like that कि only electrons जो है उनके पास ये wave correct particle nature तो clear है ही है. So wave character सिर्फ electrons के पास ही नहीं है. We can say every material particle like protons and neutrons, hydrogen molecules, helium atoms, they also show diffraction, suggesting that de Broglie's hypothesis applies to all material particles. Now, जो हमारी material particles है या day to day life में जो हम particles देखते हैं, why are we not able to detect the wavelength या why are wavelength associated with these particles या इनका wave nature हमें क्यों नहीं पता चलता है? We will do a couple of calculations for it. So, our point is why are wave effects undetectable in case of microscopic particles? Let us try and just do a couple of mathematical calculations जिससे शायद हमें clear हो जाए कि ऐसा क्यों होता है. चलिए, let us try to calculate the de Broglie's wavelength of an electron moving with the speed of 10 raised to the power 6 meters per second. So, हम ये formula use करेंगे. We have to determine the wavelength. H is Planck's constant. M is the mass of the electron and V is the velocity of the electron. Right? Planck's constant की value जो है, H की value it is 6.6 into 10 raised to the power minus 34 joule second. Mass of the electron is 9.1 into 10 raised to the power minus 31 kg. And velocity of the electron is 10 raised to the power 6 meter per second. जब हम ये calculation करेंगे, what will be the answer? The answer will be 7.25 angstroms. और इस रेंज में एंगस्ट्रॉम्स की रेंज में हम वेवलेंथ को डिटेक्ट आराम से कर सकते हैं, क्योंकि हमारे इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम में भी हम बात करते हैं रेडिएशंस की, इनके वेवलेंथ की इन टर्म्स ऑफ एंगस्ट्रॉम्स. Now let us try to do the same thing with a macroscopic particle. हम देखते हैं उसकी वेवलेंथ कितनी होगी. Let us try and calculate the de Broglie's wavelength of a particle of mass 10 grams, moving with the speed of 10 meters per second. Again, we'll use the same formula. Lambda is equal to h by mv, h Planck's constant, M is the mass of the ball, 10 grams. SI unit use करना है तो we'll convert it into kilograms. We'll multiply it by 10 raised to power minus 3 kg. And this velocity is equal to 10 meter per second. तो हमारा आंसर क्या होगा? Our answer is 6.6 in 10 raised to power minus 33 meters. कितनी कम ये वेवलेंथ है। यही वजह है कि जो हमारे मैक्रोस्कोपिक पार्टिकल्स है उनके साथ जो एसोसिएटेड वेवलेंथ्स होती है ये इतनी कम होती है कि जो हमारे प्रेजेंटली इंस्ट्रूमेंट्स है इट इज ऑलमोस्ट इम्पॉसिबल टू डिटेक्ट देम विद दीज इंस्ट्रूमेंट्स। दैट्स व्हाई इट मेक्स इट अनडिटेक्टेबल, राइट? जो एक्सट्रीमली स्मॉल साइज वेवलेंथ का है ये वेव इफेक्ट्स को अनडिटेक्टेबल बनाता है इन केस ऑफ मैक्रोस्कोपिक पार्टिकल्स। In our next lecture, we will just try to relate this wavelength with the kinetic energy and the potential energy of the electron. I hope this lecture was useful. If you find these lectures useful, please like, share, and subscribe my channel.